We have page 188, number 51. 25-kilogram child on a 2-meter long swing is released from rest when the swing supports make an angle of 30 degrees with the vertical. So if we draw the situation, basically what you have here is you have a person on a swing, right? Maybe that's what a swing looks like. And this is a 25-kilogram child. We know the angle right here is 30 degrees. We know this distance is 2 meters. So when he swings down, he's going to go like this, right? You guys have been on a swing before, and then it's back up like that and stop. So basically, if I draw a line from here to here, that's where the child is at the bottom of the swing. Well, is there a difference between his height where he is now and here? And the answer is yes, there's a difference, and that height is how we get our potential energy. That height, because the A part, the A asks for potential energy. We know potential energy equals mgh. Well, we already know 25 kilograms, that's good. G is 10 meters per second squared, that's a given, so all I have to do is know H, and I'll get the answer. So, how do I do that? Well, let me go up here and get a different colored pen. From here to here, I can find this red distance using 2 meters times cosine of 30. 2 meters, because this is hypotenuse, this is adjacent. Put that in your calculator. 2 meters times cosine of 30 degrees. Be sure you're in degree mode, and you'll get 1.73. Well, now that means I can find this, right? Because the distance from here to here is 2 meters, so it's going to be 1.73 minus 2 meters, and that's going to give me 0.27 meters. So this child is 0.27 meters above the bottom position, which we're going to call 0, right? We get to call 0 where we want to call 0. We're going to call 0 there, so that means this is 0.27 meters. So what I do, I put 0.27 meters in here. When I do that, I get 68. Now, if you look in the answers in the book, they have 66. That's because we use 10 instead of 9.81. Okay, that's A. B, they asked for the speed of the child here. Now, again, we could use Newton's second laws and all those kinematic equations, but remember how easy this is. We know that the initial potential equals the final kinetic. Kinetic is the only equation we have with velocity in it in this chapter. So basically, 68 joules, that's potential energy initial, has to equal the kinetic, which is 1/2 mv squared. So 68 joules will equal 1/2 times 25 kilograms times v squared. So v, if we solve this, put in your calculator, you're going to 2 times 68 divided by 25, take the square root, and you're going to get 2.3 meters per second. Now, C asks for the total mechanical energy, and you're going, oh no, I don't know that. How do I find that? What's the equation for total mechanical energy? Well, total mechanical energy, remember, doesn't change. If he starts out with 68 potential here, he ends with 68 here. What kind is it? It's kinetic. In between here would be 68 joules of kinetic and potential, but when you add them together, you get 68. So, total mechanical energy is a constant. It's 68 joules. The type of energy just changes. We go from potential to kinetic, back to potential, back to kinetic. In between here, we're going to have a mixture of kinetic and potential, but when added together, they're always going to equal 68. Did he ask an interesting question? In real life, we do have friction, and we're ignoring that for the most part in this chapter. So I know that my total mechanical energy is 68. Well, they asked the question, what if the child is only moving with 2 meters per second down here at the bottom instead of 2.3? Well, that means my kinetic energy is 1/2 mv squared, which is 1/2 times 25 kilograms times 2.3 meters per second squared. That's what that means. No, I'm sorry, 2.0. Messed up there. Remember, they changed the velocity to 2 meters per second, not 2.3. Should be 2.3, but it's only 2. 2.0. So when I do that, I get a velocity, or I'm sorry, not a velocity, an energy of only 50 joules. Well, that is negative 18 joules less than 68. That is the answer to that question. That is how much energy was lost due to friction, which in this case would be air resistance. So he lost 18 joules. So that is how you do number 51 on page 188.